Welcome to chapter 3.5. Here we will study exponential and logarithmic models. Okay, so what we are going to do here is take all of the information that we have learned in the previous three sections of chapter 3 and apply that information to real life situations. All right, applications of everything we learned. The good news is there's nothing else for you guys to memorize or remember. You have all the skills to solve these problems moving forward. They're just going to take a little bit of critical thinking and some problem-solving ability. So, the two most common types of mathematical models involving exponential functions are exponential growth and exponential decay. These models can be written with a base of e. Always be written with a base of e. That's pretty cool. Any exponential growth model can be written as a base of e. Any exponential decay model can be written as a base of e. And so exponential growth can always be modeled as y equals a times e raised to the bx, where b is greater than 0. Exponential decay can be modeled as y equals a e to the negative bx, where b is greater than 0. Okay, so in the next couple problems, we're going to be coming up with a few different models for exponential growth and exponential decay. Notice that in these equations, when you are coming up with models, you need to solve for the constants in the formula, right? Again, think back to your algebra classes. If you were trying to come up with an equation of a line, right? A lot of you guys like slope-intercept form, y equals mx plus b. In order to come up with the equation of this line, you had to solve for the constant m, which was your slope, and you had to solve for the constant b, which was your y-intercept. All right, so when we're coming up with models here, it's going to be very similar, okay? Except our constants in this case are going to be a. You're going to have to solve for a, and you are going to have to solve for b. Your variables are still x and y. X is your independent variable. Y is your dependent variable. And e, well, e is actually a number. E is Euler's number, which we studied earlier on, okay? E is a number. Don't worry about solving for that. That just represents the number e. Your constants are going to be a and b that you must solve for. All right, so the number of bacteria in a culture is modeled by the function n of t is equal to 250 e to the kt, where t is the time in hours. Find the constant k if the population of bacteria is 500 when t is equal to 10. So notice that this is actually a model or a partial model of exponential growth, right? Here we have y equals a times e raised to the bx. Now, instead of x as our independent variable, we're using t to represent time. Instead of y, we have n, which represents the number of bacteria. And we already have our constant here in front, a. A is going to be 250. So what we're actually solving for is this constant k, or what would have been b on the previous slide. So it says find the constant k if the population of bacteria is 500 when t equals 10. Well, what does this mean? This tells me that if I plug in 10 into my function for t, I need to get out 500. N of 10 is equal to 500. All right, if I plug in 10 for t into my function, I'm going to get out 500. And so notice that now we are trying to solve for k. And where is k located? It's located in the exponent. We have just generated an exponential equation. And by now, you guys all know how to solve exponential equations. How do we solve exponential equations? We need to try to isolate the exponential quantity. So our first step here, to isolate e raised to the 10k, we're going to divide both sides by 250. This gives me e to the 10k is equal to 2. And now, because our unknown, our value of k, is in the exponent, it is being exponentiated, we need to do the inverse operation of exponentiation to bring it out of the exponent, to undo that exponentiation. Well, To do so, we're going to take the natural log of both sides. Remember, logging is the inverse operation of exponentiation, and we want to log with the same base as the base of our exponent, which is e in this case. So we have the natural log of e to the 10k is equal to the natural log of 2. These inverse operations on the left-hand side cancel out, leaving us with 10k is equal to the natural log of 2, meaning that k is equal to the natural log of 2 divided by 10. All right, so there we have our constant k. We can plug that back into our formula, giving us n of t is equal to 250 e to the natural log of 2 over 10 times t. Notice all I did is I substituted k back into our formula here. This is n of t equals 250 e to the k times t. 250 e to the k times t. All right, and so this function will give us the population at any time. Now, let's do some algebraic manipulations to make this expression look a little bit better, right? It's pretty ugly as is. So hopefully you guys agree that I can reorganize this multiplication here in my exponent and rewrite that as 250 e to the natural log of 2 times t divided by 10. All right, instead of dividing the natural log of 2 by 10, I can just move that underneath the t. All right, now let's think about properties of exponents. Exponents raised to exponents means that we multiply the exponents. Notice that these are connected by multiplication. So another way of writing this would be e to the natural log of 2 raised to the t over 10. Again, exponents raised to exponents, you would multiply these two exponents, which is the exact same thing that we have here. Now, why is this going to help us out? Well, here we have e raised to the natural log of 2. I am exponentiating a log with the same base. Those are inverse operations of each other, which means they cancel out, leaving us with 2 inside of these parentheses. We have n of t is equal to 250 times 2 raised to the t over 10. Right, there we have our simplified form of our population function. All right, this population function is a model of exponential growth, and we have solved for all the necessary constants in there. All right, n of t is equal to 250 t to the t, times 2 raised to the t divided by 10. Okay, so let's take it one step farther now. How long does it take for the population to triple? Well, tripling the population means that we need to know the initial population first, right? What is the initial population? Initial population means the population at time t equals 0, right? Time starts at 0. So we plug in 0 for t, and if we plug in 0 for t, well, 2 to the 0 power is going to be 1. 250 times 1 gives us 250 as our initial population. And what do we do next? We want to find the time when the population is going to be 750. Why 750? Because 750 is 3 times the initial population. So, what can we do? We can set up an exponential equation. We have our population formula. N of t is equal to 250 times 2 raised to the t divided by 10, and we want to know when that is equal to 750. We take our population function and we set it equal to 750. All right, now we can begin to solve for t. Well, notice we have generated an exponential equation. To solve exponential equations, we want to begin by trying to isolate this exponential quantity. We start off by dividing by 250. Dividing both sides by 250 gives me 2 raised to the t over 10 is equal to 3. Now notice our value of t is being exponentiated. How do we undo exponentiation? By logging. And in this case, we are going to log both sides with a base of 2. Log base 2 of 2 raised to the t over 10 is equal to log base 2 of 3. The inverse operations of log base 2 of this exponential quantity with a base of 2 are going to cancel, leaving us with t divided by 10 is equal to log base 2 of 3. And finally, to solve for t, we are going to multiply both sides of the equation by 10, giving us t is equal to 10 times log base 2 of 3, which is approximately 15.85 hours. Okay, if you were to plug in 10 log base 2 of 3 into your calculator, you would get 15.85 hours. That is how long it takes for the population of the bacteria to triple from its initial population. All right, there you have our first application of exponential growth.